Hi, everyone. In today's lesson, we are going to learn about something called centripetal acceleration. This is our first lesson in the lessons we're going to do this week, which are all focused on circular motion. Okay, so that's the direction we're going, and we're going to start with centripetal acceleration. So when we think about acceleration, we remind ourselves that acceleration is a vector, so we'll put a little vector hat on it. And when we define acceleration, we define it as our change in velocity divided by time. So how fast our velocity is changing is our acceleration. Now, if I had a velocity, I'm going to choose a velocity here. I'm just going to make one up. Let's say 36.4 meters per second. That's not actually a velocity because it only has a magnitude. So a velocity, being a vector, needs magnitude and direction. So I'm going to add a direction here. I'll say south, 46 degrees towards the east. Now that is a proper velocity vector. Now, if that velocity vector is to change, that's what we call acceleration. And I could change it by increasing the magnitude. I could change it by decreasing the magnitude. Anything that changes the magnitude of velocity would be an acceleration. Changing the velocity and how fast it changes over a certain period of time tells us the acceleration. But I don't just have to change the velocity. I could also change the direction. If I keep my magnitude of my velocity, we call that the speed, consistent, but my direction is changing, then I'm still accelerating. This is something that is a little tough for students to wrap their heads around. But if I have a car and that car is going around an oval racetrack that looks kind of like this, right? And we're going around and around the racetrack, I could keep the same speed. Let's say I kept a speed of 58 kilometers per hour the whole entire time I'm driving around that oval racetrack. The fact that my direction is changing as I go around means I am still accelerating. Okay, so acceleration is still happening. So that's what we are. That's what we are looking at here. Now, the name centripetal, centri and petal, has the following meaning. Centri means center, and petal means seeking. So in this case, we are talking about center-seeking acceleration. And the next lesson we're going to have is about centripetal force. Okay, let's dive in on this stuff. So first of all, you can find this stuff in chapter 3.2 in your textbook. But an object that's moving in a circular path at a constant speed, we say that that's undergoing uniform circular motion. So constant speed in a circle, we call it uniform circular motion. But it is accelerating because the direction is changing as it goes around that circle. So it is still accelerating. We have a special name for this type of acceleration. We call it centripetal acceleration, and we use AC, subscript C, to show centripetal acceleration, where we only have the direction changing. So here's a picture of some circular motion. We can see that things are going round and round and around the circle. And during this circular motion, if we have speed v, at any point, that's going to be our instantaneous velocity at any point in the circle. We're going to have our centripetal acceleration at 90 degrees. So our acceleration is always going to be at 90 degrees to our velocity. And our acceleration is always going to be pointing towards the center of the circle. And our velocity at any instantaneous moment will always be tangent to the circle. If the object is here, the velocity is going to be tangent to the circle like that. If our object is here, the velocity is tangent to the circle like that. But each time, our acceleration is always pointing towards the center of the circle. And since they are perpendicular to one another, our acceleration never changes the magnitude of the speed, it only changes the direction. Okay, we need a formula for this. Now, for our formula, it's only going to tell us the magnitude, not the direction. So you'll notice this formula isn't going to include vectors. So here's our formula here for centripetal acceleration. We're going to take our speed and we're going to square it, and we're going to divide it by the radius of the circle. And that's going to tell us our centripetal acceleration. Now you'll notice that speed is meters per second squared, or sorry, just meters per second rather. So when we square speed, we're going to end up with meters squared over seconds squared, and we're dividing it by radius, so that's going to be meters. And one of the meters on top will cancel out, and the meter on the bottom will cancel out, and we're left with meters per second squared is our units, which we know are the units for acceleration. And our direction, we're always going to say towards the center. So we don't need to put you'll notice in our formula, they don't have vector hats because they're not using vectors. We're only finding the magnitude. And we happen to know that it's always towards the center. Okay, let's develop some further formulas for this. We know if we do one full circular revolution, the amount of time for that, we call that the period. And this is something you would have learned in grade 11 physics when you did waves, vibrations, and sound. We use capital T for period. So period is just the amount of time for one full revolution, one full cycle. We call that the period, and we measure it in seconds as our standard SI unit for that. And the distance traveled is going to be the circumference, and we have a formula for that. Our formula for circumference is 2 times pi times the radius. So therefore, we can say that the speed of the object is going to be distance over time. Distance is 2 pi r. The time is the period. That's the amount of time for one full cycle. So that's going to be our formula that we can use to calculate the speed. So we can actually sub that into our equation, right? We had our equation that we looked at on the last page, and we're going to say, okay, we're going to sub in 2 pi r over the period for where speed is. We'll square it and then divide it by the radius, and this is what we're going to end up with. Our equation, when we have the period, that's the amount of time for one full cycle, is going to be this: 4 times pi squared times the radius divided by the period squared. So anytime we're given the period, something says the period is, I don't know, like 16 seconds. That's what we would sub in for that capital T. Yeah, that's the amount of time for one full cycle. Okay, don't forget to square it. Lots of students, when they work with these formulas, they miss that exponent there. That's very common to miss that. We know that frequency is the amount of cycles per second in the amount of rather than the amount of seconds per cycle. It's the inverse of period. You would have learned this last year in grade 11 physics when you did waves, vibrations, and sound. So we can substitute our frequency in for our period, and our frequency is going to be up here on top. Again, it is squared. Watch out carefully and make sure that you don't miss that. So these are the two formulas we can use when we're trying to find the centripetal acceleration if we're given the period or if we're given the frequency. We're going to use these two formulas to calculate it. Okay, let's jump in on a couple of example problems and try them out. Here's our first example problem. It says a car executing a circular turn of radius 80 meters has a centripetal acceleration of 5.0 meters per second squared. How fast is it traveling? So we're talking about a part of the road that happens to be circular in shape. They're going around a corner that happens to be circular, and the radius to where the car is from the center of what would be that circle is going to be 80 meters. And we want to figure out what's going on with this car. So first of all, we say, okay, we know this is centripetal acceleration. We can write down some of the things we know. First, we can say our centripetal, actually, let me go to purple pen here. I can say my centripetal acceleration is going to be 5 meters per second squared. Now you notice I'm not putting directions in because I'm just calculating the magnitude here. We know the direction of the centripetal acceleration will be towards the center of the circle. Our radius is 80 meters. I notice my units match up, meters per second squared and meters, that's all good. How fast is it traveling? My speed is the thing I want to know, but I don't currently know. My formula is centripetal acceleration is the speed squared over the radius. I can sub my values in for 5 for centripetal acceleration and 80 for my radius. I can multiply the 80 up onto the left, 80 times 5, and I say, okay, I'm going to have my speed squared is 400. And then I can take the square root of both sides. So then I end up with plus or minus 20. Now I know it's going to be the plus in this case, though I want the positive number when I do the square root. 400 squared is 20. And how many significant digits do I need to write this to? Say, okay, I'll do my rounding off for sig figs. It looks like I have 3 significant digits here, and I have 2 here. So it's going to be 2 that I rounded off. So I'll write it as 2.0 times 10 to the 1 meters per second. And I don't need to put in a direction because I'm only finding speed here. I know that it's going to be tangent to the circle. That's going to be my instantaneous speed. Okay, so that's just using the base centripetal acceleration formula. Let's try our next one here. A tether ball is attached to a 1.5 meter long rope and whirled in a circular path with a frequency of 1.25 hertz. That means 1.25 full spins every second. So if I'm looking from above, here's my pole, here's the rope, here's the tether ball, and I notice that it's going around in a circle like this. That's not the most perfect circle that ever was drawn, but good enough. 1.5 meters is my radius of my rope, and I know my velocity is going to be going like that, and my centripetal acceleration is going to be towards the center there. So I'll write down the things I know and I need to know. First, I'll say my radius is 1.5 meters. I know my frequency because that's given in the question. It's 1.25 hertz, 1.25 cycles per second. So we know the units for frequency is actually per second, or second to the -1, right? But we give it its own special name. We call it hertz. And I say, okay, looks like I'm going to be using my formula for centripetal acceleration that includes frequency. And that's what I want. I want the acceleration, so I'll put a question mark there. So we have a formula for this. We're going to say centripetal acceleration, the magnitude at least, is 4 times pi squared times the radius times the frequency squared. Don't forget to square the frequency. Students forget that all the time. So that's going to be 4 times pi squared. Those are ones I'm just going to plug in using my calculator. I have a pi button on my calculator. I have 1.5 for the radius, and for the frequency I have 1.25, and it's squared. That's just some calculator work I'm going to plug through, and I'm going to end up with 92.5 meters per second squared. I'm going to want to round that off though. So we'll say, okay, my centripetal acceleration, when I round that off, looks like I got 2 significant digits here and I got 3 here. So I'm going to round it off to 2 sig figs. So that's going to be 93 meters per second squared. Now this does ask for the centripetal acceleration, right? If it just asks for the magnitude, then I would leave it as this, but it also asks for the direction because it just says centripetal acceleration. That has to include direction. So I'm going to say towards the center because it is constantly changing, but I know the direction is always going to be towards the center. Okay, now let's put a box around that. I'm tired of having to draw boxes poorly, so let's have a nice one like that. There we go. Okay, so that's my finding my centripetal acceleration. You might look at that number and say, 93 meters per second squared? That seems, Mr. Roy, that seems like a crazy high number for an acceleration. I'm used to it being like 1.5 or like 2.3 at the most. It's true. Centripetal accelerations will give you gigantic numbers. For things like a tether ball or a car or whatever, numbers that you won't seem used to and will be counterintuitive to what you're used to in terms of the size of accelerations. So just be aware of that. Let's have a look at our final one here. Determine the centripetal acceleration of the Earth orbiting the Sun. Now, the Earth does move in an ellipse, not in a circle, but it is close to a circle. So we're going to approximate it as a circle for our problem here. The Earth's radius of orbit is 1.49 times 10 to the 11 meters. You say, okay, I did pull this out of the textbook, right? You can get this number just straight out of the appendix in the textbook, or you could look it up, for example, on Wikipedia. Please don't ask ChatGPT for planetary data. ChatGPT will often hallucinate data like this and will give you incorrect numbers. So please use something like Wikipedia, which is extremely reliable. Now, find that students that are in the generation most of you are in have been told by their elementary school teachers that Wikipedia is unreliable because it can be changed by users. This couldn't be further from the truth in terms of scientific information, and it's unfortunate that a lot of students have been taught that lesson. Wikipedia, in terms of science information, is actually an extraordinarily reliable source. It links to all of its sources at the bottom, and the people who will watch the pages closely for scientific data tend to be the people who are experts who are working in that particular field of study. So, Wikipedia is extraordinarily reliable. Please consider it an excellent source for scientific information. Um, Ignore if you've heard otherwise, because Wikipedia, in the age of AI and AI hallucinations, Wikipedia is the gold standard for sources of information like this. Okay, and your textbook is a good one too, right? It's got this planetary data. So we say, okay, for the acceleration here, I've got the radius, right? The radius is 1.49 times 10 to the 11 meters. Okay, cool. I want to find the centripetal acceleration. I don't know what it is. What's my third thing here? I know I'm going to be using the formula because I'm dealing with the Earth moving around the sun. So I need either the frequency or the period. The Earth, like it takes a long time to get around the sun. So using the period probably makes more sense. Now, do we know the period? How long does it take for the Earth to go around the sun? We actually do, right? That's a pretty simple thing. It's 365 days. But because of the leap year, it's not actually 365, right? It's actually 365 and a quarter. 365.25. That's why every 4 years we have a leap year, because we have to account for the fact that it's actually 365 and a quarter days. Now, we're going to need to do some conversions to get this turned into seconds so that it can match up with our meters that we have above. So let's do that. Let's say, okay, I know if I put days on the bottom and I put hours on the top, in one day there's 24 hours. So I can get rid of days and days. And we say, okay, I want to go from hours to minutes. So let's put an hours on the bottom so it'll cancel out and a minutes on the top. 1 hour has 60 minutes. Hours are gone. Now I say I want to get rid of minutes and turn it into seconds. So I'm going to put minutes on the bottom so it'll cancel out the other one and seconds on the top. 1 minute contains 60 seconds. You'll notice I'm always filling in the bigger unit first and I'm putting a 1 next to it. That can make it easier to remember. 1 day, 1 hour, 1 minute. And then the smaller unit is the one I'll fill in second. Minutes are gone, minutes are gone. Now we say, okay, 365.25 times 24 times 60 times 60, and this is going to give me a value in seconds. And I'll say, okay, this works out to 3.156 times 10 to the 7 seconds. So big number of seconds, which makes sense. It's an entire year of going around the sun. Okay, now let's do our calculation. We know our formula we're going to use for this, for centripetal acceleration with period, is 4 times pi squared times the radius over the period squared. Now we're ready to jump in and start doing our actual calculation. Here we go. I'll say, okay, that's going to be 4 and pi squared. I'll leave as is because I can plug those just as numbers into my calculator. My radius is 1.49 times 10 to the 11. And my period is going to be 3.156 times 10 to the 7. Now, I've made a mistake. See if you can spot what it is. If you said, hey, Mr. Roy, this number should be squared, you're exactly right. Again, the most common mistake I see students make is forgetting to square that. Please be cautious and make sure that you are doing that. Okay, now I'm just going to hammer this through my calculator. I know I'm going to end up rounding this off to 3 significant digits. So let's plug in our number and see what we end up. Works out to 0.00590570, blah, blah, blah. Keeps going. Sorry, this, I got to be really cautious, is a squared, not a cubed. Okay, so I say I'm going to round this off to 3 significant digits. So we'll go 0.00591. That's in meters per second squared. You might say that seems like a really low number. And it is, because the Earth, if you look at it in any given moment in that giant circular orbit, looks kind of like it's going straight. It is curving, but it's such a large circle that the change in direction is actually quite slow compared to the size of the circle. So it is a very low number. And we need a direction on here. So we're going to say towards the center, which is towards the sun. Towards the sun. And let's put a box around it to show that that is our final answer. There we go. Okay, so I hope those 3 examples help. Time for you to do a bit of practice and gain some skills with calculating centripetal acceleration. I want to remind everybody our instantaneous velocity is always tangent to the circle. Our centripetal acceleration is always towards the center, and our centripetal acceleration in circular motion is only changing the direction. It's never changing the speed of the spinning thing. Good luck, work hard, and let's build those skills.